The moment when the Virtual Telescope Project publicly released crisp new images of 3.I/ATLAS struck as one of those rare events in astronomy that truly jolts all of us, professionals and enthusiasts alike. After months of tracking this interstellar visitor, observers tuned in as the project streamed remote exposures taken on November 5, 2025, from their robotic unit in Italy, capturing the object just after its conjunction with the Sun and reopening a window of observation for what might well be the most significant such visitor in recent human memory. From the moment the first frames appeared on screen, the expectations had already been elevated. This object, which entered our solar system from beyond and is only the third confirmed interstellar object ever to do so, had already stirred intrigue thanks to earlier observations from the James Webb Space Telescope, Hubble Space Telescope, and others. Among the key revelations, 3.I/ATLAS displays an extraordinarily high ratio of carbon dioxide outgassing relative to water, far beyond what typical comets display. Now, the Virtual Telescope Project's new imagery adds fresh dimension to what is already a transformational discovery. The image posted shows the diffuse coma of 3.I/ATLAS, clearly in focus. Despite the challenge of near-horizon twilight and a nearly full moon setting, the team managed to average 1,200-second unfiltered exposures to give the community a nearly live view. What renders these images so compelling is not only the rarity of an interstellar object, but also how the visual data affect our understanding of what such an object could tell us about origins, composition, and cosmic history. The Virtual Telescope Project has opened its robotic remit to the public in ways few observatories have, inviting people to witness the live feed and encouraging global engagement. When 3I/ATLAS was first spotted on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System Survey Telescope in Chile, there was immediate excitement because it already held a hyperbolic orbit and thus had to be extrasolar in origin. From that point onward, each new observation carried the weight of a once-in-several-decades cosmic opportunity. The implications of the new imagery from the Virtual Telescope Project are broad and profound. First, and perhaps most obviously, they provide a renewed window of observability. Because the comet passed near solar conjunction, many observatories were constrained or blind to it for a period. But now the object is emerging again, allowing fresh data acquisition at a critical moment in its trajectory. The timing matters because what we observe as the object departs can tell us about how its surface and coma react to solar heating, to changing insolation, and to the solar wind environment. Second, these images allow a refinement of models of its physical structure and behavior. Earlier data from Hubble had placed the nucleus diameter somewhere between roughly 0.44 kilometers and 5.66 kilometers, and highlighted a teardrop-shaped cocoon of dust off the nucleus. The Virtual Telescope's imagery adds a layer of observational continuity, showing the object in a state post-perihelion, so that comparisons across time, pre- and post-sun approach, can help determine how dust jets and coma morphology evolve. Third, the release underscores the role of participatory astronomy. The Virtual Telescope's live feed means that observers around the world can log in, witness the event, and potentially contribute visually or via data sharing. This democratizes what historically was the province of large observatories only. It also sets a precedent. When interstellar objects arrive, making the event accessible engages more minds, raises more questions, and likely will accelerate discoveries. One of the more intriguing scientific threads coming up revolves around the unusual composition of 3.I/ATLAS. The JWST observations found a CO2/H2O mixing ratio of approximately 8.0 plus or minus 1.0, which is far above typical comet values. This suggests that the nucleus may be intrinsically CO2 rich, which in turn may indicate that 3.I/ATLAS formed closer to a CO2 ice line in its parent protoplanetary disk, or was exposed to more radiation than typical solar system comets. The virtual telescope's new images provide a fresh vantage point, from the morphology of the coma to tracking how the outgassing plume evolves. These visuals help connect compositional inferences with structural behaviors. The new images also heighten attention on how 3I/ATLAS interacts with solar radiation and the solar environment. In previous observations, the object displayed a sun-facing plume rather than a classic tail, meaning dust and gas are being ejected preferentially on the side facing the sun, rather than being blown directly away. The virtual telescope's work captures the object after it has passed perihelion and is moving outward, giving scientists a chance to observe its anti-solar tail emerge more clearly. That shift from sun-facing plume to extended anti-solar tail is a hallmark of dynamic changes in comet behavior. Another implication lies in the age and origin of the object. Some analyses suggest that 3-point I/ATLAS might be billions of years old, perhaps older than our solar system itself. The new imagery supports this narrative by showing the structural resilience of the object. If it indeed remains intact and active, despite traveling across interstellar space, those visual traces of dust and coma help build a picture of what aggressive survival in deep space looks like for icy bodies. The combination of high-definition imaging, widespread observational access, and time series tracking means researchers can begin to treat 3I/ATLAS not just as a flyby snapshot, but as a living experiment in how interstellar bodies respond to solar heating and radiation. On a more conceptual level, the event stimulates reflection on how much we still don't know. If interstellar objects are more common than previously thought, and 3I/ATLAS may just be the most conspicuous example, then the mechanisms of their ejection, survival, and passage through other star systems become vital to our understanding of planetary system evolution. Every time one passes through our region, we gain direct empirical data. The Virtual Telescope Project's imagery ensures that such empirical data is more widely available, more engaging, and more integrative across amateur and professional boundaries. The timing could not be more poignant. As 3I/ATLAS recedes from the sun and heads out toward the outer reaches of our system, the window for gathering high-quality images is narrowing. That makes each new frame worth its weight in gold. The imagery released now will form part of the baseline against which future observations by JWST, Hubble, ground observatories, and robotic networks will compare. Researchers will look for changes in brightness, changes in coma shape, changes in dust yields, changes in tail length. The virtual telescope's contribution provides a data point at a key moment after perihelion, emerging from solar conjunction and back into observable sky. There is also a subtle but powerful implication for public science engagement. When an organization like the Virtual Telescope Project opens up its observations in near real time to a global audience, it fosters a shared sense of wonder and involvement. Observers in Cairo, Nairobi, Arizona, Melbourne, all can log in, watch the feed, perhaps screenshot, share with friends. The sense that we as a species are watching a visitor from another star system live is evocative. That sense of global participation is part of how science builds culture, curiosity, and the next generation of scientists. From the standpoint of astrophysical modeling, the new images also help refine the non-gravitational forces acting on the object. Objects like 3I/ATLAS, especially if they outgas strongly in one direction, experience minute thrusts that can change their trajectory in subtle ways. The images from the virtual telescope allow for better tracking of coma morphology, and when combined with positional astrometry, refining the model of those forces becomes possible, which in turn helps us better understand interstellar object dynamics, survival, and the transition from interstellar space to our solar system. Moreover, as more images are collected, scientists will compare 3I/ATLAS with previous interstellar visitors, 1I/Oumuamua and 2I/Borisov. Each one came with its own mysteries. Oumuamua with its odd shape and acceleration. Borisov with its comet-like behavior but beyond anything seen earlier. Now 3I/ATLAS is different again. Massive, perhaps CO2 rich, active, and captured by both professional telescopes and the accessible virtual telescope feed. By layering the new images into that comparative framework, researchers can begin to ask whether these three are representative of different subpopulations of interstellar visitors, or if they are simply the tip of a larger, unknown iceberg of extrasolar debris.